All right, in this lesson, we're going to look at what might be a new concept for you. It is called absolute value. Now, down the road, absolute value might seem like a bit of a troublemaker. It might seem to complicate things whenever it shows up. But the key to keeping absolute value simple is to always think of it in terms of its definition. And it's actually a very simple definition. Absolute value is simply the distance that a number is from zero. That's it. When we talk about the absolute value of a number, we're talking about how far that number is from zero. Now, the absolute value of a number is always positive. It doesn't matter if we're talking about numbers on the negative side of zero or on the positive side. When we refer to their absolute value, that is their distance from zero, we always use a positive number. And we actually have a special notation for absolute value. And it just looks like two bars surrounding whatever it is you're taking the absolute value of. So here we can see that if we're taking the absolute value of a number x, we enclose x in two bars. And that denotes the absolute value of x. So let's do some examples. First one is absolute value of 7. Well, what does that mean? Well, when we take the absolute value of 7, we just need to ask ourselves, how far is 7 from 0? Well, it's 7. 7 is 7 away from 0. Let's try another one. The absolute value of negative 5. Just think, how far is negative 5 from 0? Now, I know that negative 5 is to the left of 0 on the number line, but that doesn't matter. We just want to know, using a positive number, how far negative 5 is from 0. And of course, the answer is 5. Now, with this one, it looks like we have an extra negative sign. Don't let that throw you off. What is the absolute value of negative 43? Well, we just got to ask, how far is negative 43 from 0? And the answer to that is 43. So the absolute value of negative 43 is just 43. But we have to make our answer negative because we have this negative sign here. So the final result is negative 43. Let's try another one. What is the absolute value of negative 12 plus 4? Well, it's just asking how far is negative 12 plus 4 from 0. We can evaluate negative 12 plus 4, no problem. That's just negative 8. So we really are interested in the absolute value of negative 8. And how far is negative 8 from 0? It's just 8. Let's take a look at representing absolute value on the number line. So we're going to display some inequalities on the number line, starting with one that actually does not involve absolute value. This is just to get us warmed up a little bit here. So we're interested in all numbers, let's call them x, that are greater than or equal to negative 3. So how do we show that on the number line? Well, first of all, we got to make sure that we include negative 3 and all the numbers greater than negative 3 as well. And this is how we show that. Notice the solid dot on negative 3. That means we're including negative 3. And then we want everything else that's higher than negative 3 as well. So that's why we have an arrow pointing to the right. Now, what about the absolute value of x is greater than 2? Okay, don't let this confuse you. Remember the definition of absolute value. Absolute value is the distance from 0. So we are interested in all of our values, x, that have a distance from 0 that is greater than 2. Okay, one more time. We're interested in the numbers whose distance from 0 is greater than 2. Now, if you think about that, the obvious choice is all the numbers that are actually greater than 2. Any number that's greater than 2, well, its distance from 0 is going to be greater than 2. Notice we use an open circle here because we don't want to include 2. This does not include 2, just the numbers greater than 2. But this is not it, because we also have the negative side of things. Anything in that direction below negative 2 is also going to have a distance from 0 that is greater than 2. Think about that. All these values over here, they're more than 2 away from 0. So that's what our result looks like on the number line when we look at the absolute value being greater than 2. One more here. The absolute value of x is less than or equal to 4. Okay, let's think about again what absolute value really means. We're looking for numbers whose distance from 0 is less than or equal to 4. So we want all the numbers whose distance from 0 is 4 or less. Well, that's going to be all the numbers in this area here. Any number in this area here, its distance from 0 is 4 or less. As soon as I leave that region there, I'll start getting values whose distance from 0 is bigger than 4. And we do want to include 4 because of the less than or equal to sign here, so make sure we use solid dots. Okay, moving on. We can actually use the absolute value to create a new function for ourselves. Let's think about what the function y equals the absolute value of x would look like if we graphed it. Well, remember, absolute value of x is just the distance from 0. So if we had a Cartesian plane and we started choosing x values, what kind of a result would get? Well, would we get for all of the positive x values, for example, say 2, well, the absolute value is 2 in that case. So our point 2, 2 would be on our graph. If we choose an x value of 5, the absolute value of that is 5. So 5, 5 will be on the graph. So it seems like whenever we choose a positive number, the x value and the y value are the same. But what if we start choosing negative numbers? If we choose an x value of negative 2, what will we get for y? Well, the absolute value of negative 2 is 2. It's 2 away from 0, right? So the point negative 2, 2 would be on the graph. And you can probably see where this is going. We're going to get a graph that looks like this. And let's just briefly analyze that for a second. We said before, if we're choosing positive values, the absolute value of any of these numbers is going to be the same value. Absolute value of 5 is 5. That's why we get 5, 5. Absolute value of 1 is 1. That's why we get 1, 1 on our graph. The absolute value of 0 is 0. Now for the negatives, for example, 4, negative 4, the absolute value of negative 4, well, negative 4 is 4 away from 0. So the point negative 4, 4 is going to be on the graph. What's the absolute value of negative 7? It's 7. So negative 7, 7 is going to be on our graph. This is the graph of y equals the absolute value of x. What's its domain? Any real number. We can choose any real number that we want for x. We don't run into any issues with any x values. You can always take the absolute value because you're just finding the number's distance from 0. And as you can see from the graph, the range, we're talking about all the y values that are 0 or higher. So our range is any y value greater than or equal to 0. And guess what? We can transform this function just like we transform other functions, no problem. Let's take a look at a couple of examples here. Y equals the absolute value of x plus 3. Well, of course, this transformation is just a vertical shift 3 units up. So if we take that original absolute value graph and shift it up 3 units, we get a graph that looks like this. What about y equals the absolute value of x plus 4? Notice we've replaced x in our base function with x plus 4. So this is a horizontal transformation, specifically a horizontal shift 4 units to the right. And we can graph that just the way we graph transformations for all of our other functions. We'll take our base function and move it 4 units to the left. A tougher one. Okay, well, it's not really that bad. Let's take a look at this. We have several transformations here on the graph of y equals the absolute value of x. Specifically, we have 4 of them. We do have a vertical reflection, so a reflection in the x-axis. We have a vertical stretch of factor 2, and we do have a horizontal compression of factor 1/2. This looks very similar to what we're used to with transformations. Just remember, we don't have a horizontal shift of 6 units to the right. In order to see how much we're shifting horizontally, we need to common factor out whatever we have in front of x here, which is a 2. So I'll do that right now. And now we can see that our horizontal shift is actually 3 units to the right. And if you take all of those transformations, our vertical reflection, so a reflection in the x-axis, the vertical stretch of factor 2, the horizontal compression of factor 1/2, and the horizontal shift 3 units to the right, we get a graph that looks like this in the end. And I'd encourage you to try this on your own. Don't just trust me that this is the graph and what it looks like. Get a piece of graph paper, draw y equals the absolute value of x as your base function, apply these transformations, and see if you get this graph. All right, let's finish up with another way that we can write this function. If we have the function f at x equals the absolute value of x, there actually is another way we can write it. As you can see from the graph, the function y equals the absolute value of x, or f at x equals the absolute value of x, is made up of 2 lines. We have one line kind of in the quadrant up here, and we have another line, a different line in this quadrant here. Because of that, we can actually describe this function using 2 different lines. So the idea here, it gives us another way to write the absolute value as shown below, and that is that. Now, that might look a little bit strange, but let's just think about this for a minute. What function do we have right here? What is the equation of this line? Well, notice it's got the point 0, 0, 1, 1, 2, 2, 3, 3. The x value and the y value are always the same for points on this line. This is the line y equals x. Now, when do we have the line y equals x? Well, whenever we're using positive x values, we get the line y equals x. Doesn't happen over here when we're using negative x values. So we can say as long as x is positive, we really just have the function y equals x. And that's what this is saying right here. Our function f at x, or you think of it as y if you want, is equal to x. So we have y equals x as long as we use x values that are 0 or higher. What if we have x values that are lower than 0, so those negative ones? Well, this is not the line y equals x. It is a reflection of the line y equals x. You can think of it that way. You can also notice that for any point on this line, for example, this one is negative 2, 2, negative 4, 4. Notice that the x and y coordinates are opposites. This is the line y equals negative x. It has a slope of negative 1, goes right through the origin. So as long as we're talking about negative x values, our equation is y equals negative x. And that's what this is saying here. F at x, or y, equals negative x, only if you're using x values that are lower than 0. Now you might say, well, why doesn't this one include 0 as well? And the only answer I'm going to give you here is because I've included it down here, so I don't need to include it twice. Of course, you could include 0 in this piece and omit it in here, but we generally don't include it in both of them. And that's it. Now this representation here is known as a piecewise function, and in the very near future you're going to look at piecewise functions in greater detail. So this is just a little bit of a preview to what's coming up when you look at these things called piecewise functions. There you go. That's the absolute value, and never forget, it is just the distance from 0. Take care.